Hello, and welcome to the Whole Body Motion Planning Project proposal. In this project, we propose the development and simulation of a unique control scheme for quadruped robots. The goal of this controller is to effect natural and efficient motion for dynamic stability. We begin with the research conducted by Professor Dai, Valenzuela, and Tedrake from MIT's C-Cell lab. In their research, a quadratic optimal control scheme is proposed for humanoid robots that can effect this natural motion. We look to improve this controller in two ways. First, to attempt to include dynamics from research in biomechanics. Second, we also plan to incorporate an LQR funneling strategy. Finally, we have chosen to implement the controller on a quadruped for practicality, and also to demonstrate the versatility of the controller across platforms. It should be said that we mean to only simulate this quadruped motion. Current control schemes for motion planning in humanoid and other biomimetic robots is canonically overconstrained. The Asimo robot, as shown here, is a perfect example. The center of mass of the robot is commanded to be directly over the center of pressure at all times, which, although functional, does not result in a natural-looking motion. We hope with our controller to create a more natural motion for any robot platform, from any humanoid, including Atlas, to the quadruped that we plan to simulate.
A background study and a source of motivation involves the whole body planning paper by Professor Russ Tedrake. This paper overcomes the complexity and poor response time in planning with the whole body dynamics. It exploits the powerful middle ground in which it uses a simple dynamics model and a complete kinematics model, which turns out to be relatively easy and quick to plan. It also maintains the center of pressure within the contact wrench cone proposed by Hiroika et al. Instead of the traditional zero moment pole to perform complex maneuvers like navigating in uneven terrains.
We hope to further improve the ability of the C-Cell controller to mimic nature by including additional dynamics from biomechanics research. Some papers, including one by Professor Popovich in 2004, have suggested specific control strategies relying on certain biological parameters that could create biologically accurate body dynamics. We will look to add these constraints to the C-Cell optimized controller.
We plan to build the dynamics of quadruped robot. The quadruped robot has 8 degrees of freedom, 2 at each leg. To completely define the configuration of the robot, it is not enough just to define the joint values of the robot. It is also necessary that we know the configuration of the frame attached to the center of mass. We'll obtain the joint values of the legs of the robot directly from the simulator, and using these values and the position of contact points, we will find the pose of the frame attached to its center of mass. We will find the contact forces from the simulator, and with this we will find the net force on the center of mass and the momentum about it. We will be implementing the LQR controller in our quadruped robot. The LQR controller uses a quadratic cost function. The LQR controller can only stabilize those states that are near the required trajectory, or those states that are in the region of attraction. The region of attraction can be found using the cost function. That is, if the cost of a state to goal is really high, it means the state cannot be brought back to the required trajectory, or it is not stabilizable. Hence, any arbitrary path returned by the motion planner cannot be followed using LQR controller. This means such a path should be rejected and the whole planning phase should be repeated. To avoid this, the LQR controller limits are integrated in the planning phase. That is, instead of considering any arbitrary geometrically close state as a neighbor of the given state, we consider only those states that are reachable using LQR controller. That is, we take only those states that are in the region of attraction as neighbors. We can make sure that the states that we consider as neighbors are in the region of attraction if we search through what is called LQR trees proposed by Professor Russ Tedrake. The aim of this project is to plan a trajectory that involves a path through uneven terrains and to control the quadruped robot to follow this path. For example, we'll be making the quadruped climb stairs or do anything that does not involve just flat terrain. We are planning to show the final result in simulation. We are yet to decide the platform for this. We'll be using ROS or Drake or Sim Mechanics.
In this slide, we welcome your suggestions for the following questions. So far from our research, we are not able to find a ready-made model of a quadruped or a simulator that can be readily used. Also, we would like to inquire how appropriate is it to take this as a dynamics project if we are planning and controlling with the kinematic and controller constraints on a highly articulated robot, say a humanoid, whose dynamics is already modeled. Before concluding the presentation, we would like to mention a high-level schedule for our project. Firstly, we would like to decide on the simulation environment and solve the forward kinematics problem for the walker. Before the spring break, we would like to come up with a model that can be simulated in any test bed. By the end of March, we hope to develop and test the controller with LQR constraints. In April, we would like to plan with the kinematic and added controller constraints. We hope this project will give us a great experience. Thank you for your time for listening to our presentation.